Hello, Chemistry 11. Today we're going to be talking about energy in chemical reactions. This is a branch of what they call thermochemistry because it has to do with heat, either heat being absorbed or heat being released. And so thermo has to do with heat. So we have two main types of energy. One of them is kinetic energy, which we can abbreviate Ke, and that is the energy of motion. Okay, so kinetic energy, Ke, is the energy of motion. Potential energy, which can be abbreviated Pe, is energy that is stored. Okay, so two main types of energy, kinetic energy and potential energy. We also have the law of conservation of energy, which you're probably familiar, and that is that energy cannot be created nor destroyed, but it can be transformed from one type of energy into another. So what this results in is that the total energy is going to equal all of the kinetic energy, all of the energy of motion, plus the potential energy, all of the energy that is stored. And you can transform some of the potential energy into kinetic energy and vice versa, but the total energy will always remain the same. The unit of energy is the joule, 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 pronounced joule, and it can also be a kilojoule, kJ. Okay, so the joule or the kilojoule. Okay, this next little bit, it's mostly for interest. You don't have to memorize it or anything like that. Kinetic energy, there are three main types. There is vibrational, rotational, and translational. So by vibrational, what you're going to have is you could have a molecule, say like water. There we have or actually I think that one's carbon dioxide. And it might sort of wibble wobble back and forth between two different forms. And it would sort of, this middle part would move down and you'd end up with it here. And then this middle part would move up and you'd end up with it up top and would sort of go wibble wobble, wibble wobble, wibble wobble. You can imagine if I was holding my arms out to the side, if I was a little person holding my arms out to the side, I would be like this, and then I would be like this, and then I would go up, down, up, down, up, down. Okay, that's one form of vibrational energy. Another type of vibration is stretching, and if we're stretching, this is symmetrical stretching. I might go from having quite longish bonds to having quite shortish bonds. Okay, so it's as though I was taking my arms, if I was a little person, and I, brought my arms in, and I brought my arms out. Whee! Okay, the bonds stretch and flex. It's almost, I guess, as though you had a slinky in there. And then you can have asymmetric stretching. This is way more fun if I can show you in person, and probably I should turn on the video and do that, but it's like I went from here to here, right? If I'm a little person, I'm sort of punching out from one side to the other. Punch, 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 side to side, moving both my arms in and out. At any rate, not terribly important, but will come up in university, so you might as well know about it. All right, then you have rotational. Rotational is easier to imagine. You simply have this thing spinning around on its axis, or you can have it spinning around on its other axis. Okay, so it can spin in few directions there. And then finally, translational. Translational is the form that we're most familiar with, and that's if the molecule is simply moving in space. It's just moving from one place to another place. So the more a molecule is either vibrating or rotating or moving in space, the more kinetic energy it has, and the faster it moves in any of these ways, also the more kinetic energy it has. So if something is moving faster, it has more kinetic energy. Okay, so that's really the key takeaway from this thing, is if it's moving slower, it has less kinetic energy, and if it's moving faster, it has more kinetic energy. Temperature is a huge, huge important concept, okay? Temperature is a measure of the average kinetic energy. So you can think of it as temperature is the average kinetic energy. And remember, kinetic energy told us how fast or how slow the particles are moving, right? If you have more kinetic energy, it's moving faster. If you have less kinetic energy, it's moving slower. And if temperature is the average kinetic energy, if you have faster molecules, there's going to be more kinetic energy, and so the temperature is going to be higher. So faster molecules means a higher temperature. Okay, and slower molecules mean a lower temperature because slower molecules have less kinetic energy. Okay, so those are key ideas. What is temperature? Temperature is a measure of the average kinetic energy. Huge important idea that. Okay. Now let's talk potential energy. Potential energy is energy that is stored in atoms and in the bonds between atoms, and it can be released by various chemical reactions. Chemicals with a high potential energy are less stable. Okay, just like a ball at the top of the hill is less stable and has a high potential energy, chemicals with a low potential energy, just like a ball at the bottom of the hill, the ball at the bottom of the hill is more stable. Okay, and it is at a low potential energy. And remember, in nature, everything wants to move from an area of high potential to an area of low potential. And the only reason it won't is, like, let's say there was a little barrier here that kept it from doing that. Okay. Other than that, if you put the ball at the top of that hill, it will naturally want to move down unless you have some sort of barrier preventing it from doing that. Okay, and if you have a ball at the bottom of the hill, it's more stable. It won't roll up the hill unless you push it. If you put energy in and you push that ball up the hill, you can get it to go up the hill, but it won't do that naturally. Okay? Now let's talk about energy transformations. If kinetic energy is transformed into potential energy, what that means is that we're going to end up with less kinetic energy and more potential energy. And if we have less kinetic energy, that means that the molecules are going to move slower. If the molecules are moving slower, that means that the temperature is going to decrease, okay? Because temperature is a measure of the average kinetic energy. But remember, we didn't lose kinetic energy and like just have it disappear. It turned into potential energy. So we have less kinetic energy, but we have more potential energy. So the total amount of energy will stay the same. Now, if we have potential energy and we transform it into kinetic energy, what that means is now we're going to have more kinetic energy because we turn some potential into kinetic, and we're going to have less potential energy. And if we have more kinetic energy, Remember, temperature measures the amount of kinetic energy, so the temperature is going to increase. If we have more kinetic energy, we have more motion, that means the molecules are moving faster. And the total amount of energy, though, because we have more kinetic but less potential, that's going to remain the same. So let's look at this in the context of a chemical reaction. Say you have some reactants. Okay, here's our reactants. And those reactants have 2 kilojoules of potential energy. Just because stored within their bonds and stored within the electrons of that atom, there's 2 kilojoules stored in that atom that could be released or could just be hung on to. Okay, that is potential energy. Let's say that the products, okay, our products, they are different chemicals now, so they have different chemical bonds, so they're going to have a different amount of energy stored in them. And let's say that they have 12 kilojoules of potential energy stored in them. Well, in order to go from reactants to products, the products have more potential energy, so we must have that energy must have come from somewhere. What had to happen is we had to take 10 kilojoules of kinetic energy and transform it into potential energy. Okay? And we write it like this. We write reactants, which had 2 kilojoules, and then we say plus 10 kilojoules. When we write an energy term in a reaction, that's always the kinetic energy term. Okay? Energy term in a reaction always represents the kinetic energy. Okay, and the potential energy is still there. I'm just going to check and see if I wrote it down here. Yes, I did. Okay. Potential energy is still there, but we don't write it in the reaction. So it's kind of hidden. So people always think, oh my gosh, I end up with more energy in the products than I had in the reactants because now, or something, I don't know. It gets confusing because the potential energy is hidden because we don't actually write it. But here, we're going to write it, okay? So we have our reactants, and they contain 2 kilojoules of potential energy. Okay, so we have 2 kilojoules of potential energy in our reactants. Our products contain 12 kilojoules, and that's of potential energy. Okay, and where did that extra 10 kilojoules come from? That extra 10 kilojoules came from 10 kilojoules of kinetic energy. And that meant that 10 kilojoules is transformed into, of kinetic energy, is transformed into 10 kilojoules plus our other 2 from the potential energy, 10 kilojoules of potential energy. And in this process, we took kinetic energy and we transformed it into potential. That means we're going to have less kinetic energy, which means that our temperature is going to get lower. And this is where people get confused because they see, oh, I added 10 kilojoules of energy. And that we sometimes refer that to as 10 kilojoules of heat because that's going to feel warm. The particles are moving fast, so the temperature is going to be high. Well, I'm adding heat. Wouldn't that make it hotter? Here's the problem. We add the heat, which is like the kinetic energy, the motion, but then in the reaction, it is transformed into potential energy. So we had heat, and now we no longer, after the reaction, it has been transformed. It's no longer heat, it is now potential energy. So we had heat, and now we don't have heat. We had heat, now we don't have heat. So this reaction is actually going to get colder. Sounds weird. You add heat and it gets colder. Well, what's happening is you're not really adding heat. What you're doing is you're the reactants are sucking heat out of their environment. Okay? Where is this heat coming from? This heat is coming from the environment. Okay? So maybe if you're holding a flask with a reactionant, the environment is your hand. Okay? So you've got a flask, and the environment is your hand. I apologize for the terrible drawing of a hand here. Okay? The environment is your hand. And this reaction in the flask, I can't draw it because it'll get too messy, is sucking the heat out of your hand. And what does that do to that heat? It changes it into, say, some bonds in that reaction, okay? And so the potential energy is going to get higher, but that heat has been sucked out of your hand, and it's now no longer moving energy, it's now potential energy. And so your hand is going to feel colder because the heat got sucked out of it, okay? So when you add heat, it actually gets colder because you're not really adding heat, you're really sucking heat out of the environment. The reactants are sucking heat from the environment. Okay. Okay, so what does this look like? All right, we can show this graphically. Okay, when we have our potential energy. Remember our reactants had 2 kilojoules. Oh, I was going to make it bigger and I just moved it. There we go. Our reactants had 2 kilojoules of energy, and our products had 12 kilojoules of energy. So our kinetic energy comes in. Okay, here comes our kinetic energy. It comes in and it gets transformed into potential energy. So the potential energy goes up, but the kinetic energy, once we get here to this point, right here, the kinetic energy is used up. Gosh, I can't draw this. The kinetic energy is used up. Where is it now? It's now part of the potential energy. It's now stored in bonds rather than being motion. So the energy is now stored in bonds. It's not making the molecules move anymore. Okay, so what's going to happen to our temperature? Our temperature is going to decrease because the molecules are now going to be moving more slowly because our kinetic energy was used up and it was transformed into potential energy. So the temperature is going to decrease. And remember, sometimes we will refer to this kinetic energy as heat. So we've added heat, but it gets transformed into potential energy. And we're not really adding heat. Remember, we're really sucking it out of the environment. So the environment, which is what we're measuring the temperature of, it's going to get colder. Okay. This is called an endothermic reaction. And that is because kinetic energy has entered the system, endothermic. Okay, endotherm. Endo for enter, thermic for heat. So heat entered the system and transformed into potential energy. And remember what that looks like in a reaction. That would be like if I had A and I added 10 kilojoules of heat. Remember, this is sucked out of the environment. And that then gives us B. And remember, B would now have, if A had 2 kilojoules of potential energy, B now has 12 kilojoules of potential energy. And if we were to actually graph our kinetic energy, right, if we had our kinetic energy, it would start high and it would finish low, and we would have lost 10 kilojoules of kinetic energy. And remember, high kinetic energy is high temperature, and low kinetic energy is low temperature. Okay. So now, say you have some reactants in a chemical reaction, and they have 9 kilojoules of potential energy. Say that the products of that reaction, so our reactants had 9 kilojoules, say our products have 1 kilojoule of potential energy. Well, we went from a higher amount of kinetic energy to a lower amount of high amount of potential energy to a low amount of potential energy. Where did that extra energy go? We lost 8 kilojoules. Well, those 8 kilojoules of potential energy that we lost must be transformed into kinetic energy. So we gained it. We gained kinetic energy. So the system lost potential energy. We now end up with more kinetic energy than we had before. So here's the weird thing. Heat is coming out. And you know what? If heat comes out, gosh darn it, it feels hotter. This is the one that makes more sense to people usually. Exothermic reactions. This is an exothermic reaction where the heat comes out. So this is our heat. We often call that the heat term. Okay, and remember this is kinetic energy. The heat term is kinetic energy. It feels hot because the particles are moving faster because they have 8 kilojoules more of kinetic energy. Okay, and the heat is exiting the system. See, it came out of the reaction. Remember, up in our endothermic reaction, our heat entered the reaction. It went in with the reactants. Okay, so the heat enters. Here we have the heat, and here the heat exits the system. And the system is like our reaction, okay? Whatever liquid or solid or whatever it is we have, that is our system, and that is what the heat is exiting. It comes out, and so it then transfers maybe to your hand or to the air, and it makes your hand or the air hotter. Okay, so let's take a look at this again. So we have here our reactants, and they have 9 kilojoules of potential energy. We have our products, and they have 1 kilojoule of potential energy. Okay. Where did that extra 8 kilojoules go? It came out as 8 kilojoules of kinetic energy. Okay, this is heat lost by the system, by our reaction. Okay, system has an S in it. And remember, when we say it's lost by the system, that means it's just coming out. We've transformed, okay, we transformed 8 kilojoules of potential energy into 8 kilojoules of kinetic energy. And to show this graphically, we see that our reactants start at 9 kilojoules, and our products have 1 kilojoule, and that is of the potential energy. So the reactants are less stable, and the products are more stable. And the potential energy lost is going to equal the kinetic energy gained. Okay, and this kinetic, and it's weird to say this because the system is losing kinetic energy, but when in total, like the universe gained kinetic energy, it's just coming out of the reaction and into the universe. So we have made kinetic energy out of potential energy. And if we were to draw a kinetic energy graph, it would look the other way. It would go from being lower to being 8 kilojoules higher. Okay, so that would be our kinetic energy, would go from lower to higher. And because our kinetic energy has increased, we had potential energy transformed into kinetic energy, the temperature is going to increase because remember temperature? What is temperature? It is a measure of what? Temperature is a measure of the average what? It's a measure of the average kinetic energy. And we call this an exothermic reaction because heat is exiting the system. So we have X for exit and therm for heat. Heat exits the system. Kinetic energy exits the system because we transformed that potential energy into kinetic energy, and then kinetic energy exits the system. Okay, so you're going to do the reading check. All right. Reading check, reading check, reading check. La la la, la la la. Here's an answer key. Do do do, do do do, do do do. And let's see, we've been at this for about half an hour, so I'm going to leave it there for today. If you want to go ahead and read ahead on this, we will be doing this next week. Feel free to go ahead. Okay, so you guys have yourselves a great week, and we will be finishing chemistry next week. We'll be finishing off with this enthalpy stuff next week. It does become important in grade 12, so if you're taking Chem 12 next year, definitely continue on with us if you possibly can. If you've just had it and you're not taking Chem 12, well, I'm going to wish you a very happy summer, okay? And I hope that I'm there to see you in the fall, and we're all there to see each other in the fall, and that we're not stuck in our houses for the rest of eternity. Okay, have a wonderful week, and I will see you next week. Maybe in a live lesson, maybe a recorded lesson. We'll just have to see. All right, bye.